Hello everyone, welcome to Mark 1 Design EMC channel. A client of mine, Francesco, based in Oxford, asked me to make a video on how to use Spectrum Analyzer, basically the way how I use it, so he can use it more efficiently. So I thought that's a good idea, and I'm sure you can find lots of videos on the internet demonstrating how to use Spectrum Analyzer. So we're going to use a different approach. We're going to use a case study again and show you how I normally use a Spectrum Analyzer for troubleshooting. And in the beginning, we wanted to also talk about how to set up the listen, because there's also questions coming from many clients of mine, because when they set up their listen for pre-compliance work, they actually found some high ambient noise and they wonder how to eliminate those ambient noise. So we're going to start with how to eliminate ambient noise in your listen setup, then move on to how to use Spectrum Analyzer more efficiently. Okay, so let's start. As you can see here, this is a typical CISPA25 listen setup. You will probably notice here you have a big capacitor. If we look at the capacitance value of this big electrolytic cap, it is 1000 microfarad, this capacitor. Obviously, the listens are rated at 60 volts, so this electrolytic cap doesn't need to be very high voltage rated. You will also notice there are two small caps here and here across the listen terminals. Okay, so why do we need these capacitors? Well, these you can find in the show notes, which are attached. Actually, TechBox produced a very good application note explaining why we need these capacitors. What I'm going to talk about is actually, if you look at here, between my listen input and my power supply unit, I have some ferrites, right? If you look at this ferrite, which is 75 material, often very effective in the 1 meg, 2 megahertz range, I wound it in a 2-turn configuration common mode, okay? And then this is, again, 75 material ferrite, again, 2-turn common mode configuration. And then this one is a small ferrite only on the live, you can call it, or low voltage power line here, right? So why do we need these ferrites between the power supply unit and listen? Okay, here I'm going to show you. So as you can see now, the listen output here is connected to my Spectrum Analyzer via a high-pass filter here, right? Here you can see the power supply is set up as 24 volts, but I'm not actually switched on the module yet, right? So it is off. And you can see this is just the current limit setup. Now, what I'm going to do now is, if I disconnect this setup, this connection, and then replace with a normal wire connection, okay? So I'm putting here directly to my listen, and here directly to my listen, right? Simple like that. And check out here. You can see there is noise immediately picked up by the listen, and I'm actually not even I'm not even turning on the power supply unit yet. We already saw noise measured on the listen. So these noise is actually what we call the ambient noise. These noise come directly from the power supply unit. So if we measure DUT without knowing this information, this could be misleading, because this noise doesn't come from the DUT, but rather come from the power supply unit, right? So if I max hold this, you can see these are the noise coming from the power supply units. Bear in mind, I already have a high-pass filter here, so if I don't have the high-pass filter, this noise level would be 10 dB higher. So quite high level of ambient noise here, right? So now if I freeze this, I select trace 2 and clear right, okay? So now we're going to replace these two wires and using the ferrite here, okay? So if I connect here, connect here, putting things here, and again here, and putting here, right? Same setup. As you can see here, the pink trace shows the one after we use the ferrite. As you can see, the ambient noise has been suppressed. Okay, so that's why we are always having ferrite between the power supply unit and the listen. Now, depends on the power supply unit you use. We notice that with some of the customers' power supply units, not only do you need to put ferrite between the output of the power supply unit and your listen, you probably also need similar ferrite on the input cable of the power supply unit. Okay, so because sometimes these power supply units are most likely isolated power supply units. So sometimes you do need to suppress the noise on the input and output side to make sure that the common mode noise is low enough. Okay, so that's a first tip in setting up the listen to eliminate or suppress the ambient noise as much as you can. Now, with ambient noise low enough, we can move on to test the DUT using a listen setup, and I'm going to use this setup to demonstrate how I normally use my spectral analyzer. Okay, we set up our demonstration here. This is a flyback isolated power supply evaluation board from Texas Instruments. This is our active load. So this load is used so that there's no noise actually coming from this load, because it's a self-powered active load. It doesn't have any switching inside. And we power the unit up using 2 listens. And as we explained, between the listen and the power supply unit, we have some filtering here. Okay, and now we are measuring the listen output using our spectral analyzer, as you can see here. So I'm going to switch on the power supply unit, and you can see here we have 22 volts input voltage and about 663 milliamps as input current. On the output, we have about 1 amps DC current measured on the low side. Okay, and our spectral analyzer we set at preset, so that's how you get it when you power it up from the manufacturing setup. As you can see, you already can see some noise observed here. Okay, now often for switching mode power supply, lots of the noise are predominantly in the sort of lower frequency range. So we're talking about perhaps below 10 megahertz, or you sometimes have some high common mode currents sort of in the 60, 70 megahertz, or perhaps 100 megahertz. But everything should be below 100 megahertz. So the reason I said that is because the first thing of using a spectral analyzer is you need to define the frequency that you're going to measure. So first step is always define frequency. So demonstrate here, I press frequency, and then I will define a start frequency. So in this case, I'm going to start with 9 kilohertz because that's the default starting frequency of the spectral analyzer. So that's 9 kilohertz to start, and stop, I'll go to 100 megahertz. Okay, so this is my defined frequency span or frequency range of the measurement. And the next thing is I'm going to do the amplitude. So first thing is frequency, and then the next thing is amplitude. So I'm going to amplitude. Now amplitude-wise, as you can see, first is the units. Currently the unit by default is in dB milliwatts, and this is often not the units we use in EMC engineering. We prefer dB microvolts or dB microamps, depends on how you measure it. If you're using current probe, it's dB microamps. If you're using listen, it's dB microvolts. So I'm going to change the unit. So that's in amplitude, then units here. So it goes to units, and I'm changing to dB microvolts. So now, as you can see, all the units are showing in dB microvolts now. Okay, and in the amplitude, you can see there are input attenuator, which currently is set as 10 dB. And we also have, if you go to the next page, there's RF preamplifier. Okay, so really depends on your application. You select things differently. The rule is if we select less attenuator, we have more sensitivity. so we actually capture things more accurately. So for example, in this case, I can put input attenuator to be 0 dB, okay? So that's, you can see it's definitely more sensitive. You can see more just by doing that. And the spectrum analyzer basically does all the calculations. So you still have the same level of noise, but it's just more sensitive, more accurate when you see it. Okay, so first frequency, then second amplitude. Now, the third is we have to define our bandwidth. Okay, so that's in here, control bandwidth. So if I press bandwidth, as you can see here, currently the bandwidth is 1 megahertz. Now, really depends on on the standards you're trying to test against. But often in the lower frequency range, it is either 9 kilohertz or 120 kilohertz. Okay, so the lower the bandwidth, again, the more sensitivity it is. So for example, now it is 1 megahertz. If I'm going to do 10 kilohertz, let's have a look. So if I do 10 kilohertz, as you can see, the result is very different. So we set up the frequency span, we set up the amplitude, and we change the bandwidth. In this case, we adjust it to 9 kilohertz EMI resolution bandwidth. Okay, so that's all good, as we can see here. But we still can't see the frequency we expect to see, right? So the next step, right? So after frequency, amplitude, and bandwidth, next step is to go to span, okay? So here we have the menu in span mode. And if we see the button, there is scale. You can select either linear scale or logarithmic scale. So in this case, we're going to select log scale, okay? So if now I press log scale, now you can see things much more clear, right? So as you can see here, this is 100 kilohertz, this is 1 megahertz, this is 10 megahertz, and this is 100 megahertz, okay? So you clearly see the noise here, and you can see all these spikes which are related to the switching frequency of the converter. And then you can see here you have a resonance here, right? And this resonance, I bet you, is caused by the common mode current traveling on the input wires, right? So we will demonstrate this later on by clip RF current probe in these wires, and you can see the common mode current must follow the same shape as this one. Whereas in this lower frequency range, it's perhaps more differential mode rather than common mode noise, okay? So there you go. Very simple steps. If you just follow this, you will see the noise you want to see, and then you can start troubleshooting, you can get the information you want. There are some more advanced techniques of using spectrum analyzer. For example, you want to know the main dominating switching frequency of the converter, right? So let's go to marker, and then you can select 4 markers, and then you can mark them. For example, I can just select marker 1 normal, and then I can use the button to tune it. So as you can see here is 130 kilohertz as the dominant frequency, and then I can go to the next one simply by doing that. But more effective way of doing this is here you can see there's peak in the mark menu. So if I do peak, and I can select next peak, and as I select next peak, you can see the marker jumped automatically. Next peak, and then you can go back to peak left, peak left, peak left, peak left, right? And you can select the peak, which is the highest peak. And yeah, so these will make things a lot easier. Back to marker, and let's say this is our marker 1 is our main dominant switching frequency, and you wanted to see the second order harmonics, and you want to see the delta. So we can see select trace 2, or actually we can select trace 1, but rather than normal, we select delta. Okay, so when you select delta, then you have the reference you can use, and you have the delta. So if I have the reference, which is showing as marker 1 R, means marker 1 reference, and then I can do the other marker 1 as I move. You can see here. So this is my reference 1R. This is my marker 1, and then tells you they have -3 dB difference between the first harmonics and second harmonics. And then if I go to the marker, and then I can select marker table. So currently it's off. If I select it on, then I have the information I need, which is reference 1R at 130 kilohertz with the amplitude of 76.48 dB microvolts. And the delta, which is this point, is just 3.52 dB less than the fundamental one. And then you can see, then you can save this picture and then present this to your boss or your colleagues. Okay, so very effective. Okay, so yeah, as I said, these are really the basic functions of a spectrum analyzer. That is how I normally use. I don't really use many other functions which the spectrum analyzer can provide. But often, just by doing this basic setup, it will give me the information I need, and doing more advanced stuff. So we'll introduce more advanced features in our next video, and I hope you enjoyed it.